So good morning, everyone. Thank you very much for the invitation. It's a great pleasure to be back in this meeting and to be for the first time in this place. So I'm Julien Laurat. I'm professor of physics at Sorbonne University, and I'm leading a research group at Laboratoire Kessler-Bruxelles, a research group on quantum optics and on quantum information networks. As a disclaimer, I'm also the co-founder and a scientific advisor of the networking company WeLink, which is based in Paris, and I will show you a few results from time to time, which are coming also from the company. So today I would like to discuss something we all know, which is a challenge of quantum information, how we scale in the future our quantum information architectures. And I would like to discuss what are the needed capabilities and show you some experimental result that enters into this kind of roadmap. So the challenge for quantum information architectures is to scale. And one way to scale is networking. So what is networking? Quantum networking is the art, the capability of generating, distributing, allocating entanglement in a network. And we know a few applications for that, typically two main paths of research. The first one is to develop long-distance quantum communication, what we call now the quantum internet, since the paper by Jeff Kimball, and you all know also this picture from the Quantum Internet Alliance. So basically why we need that, if you want to transmit information at long distances, you cannot use this kind of classical devices to re-amplify the light, and you need to develop what we call a quantum repeater. And to develop a quantum repeater, you are going to cut the long distance in many segments. And in all of these segments, you are going to store entanglement, and then by entanglement swapping, restore the long distance. And then you can make some entanglement-based quantum cryptography or blind quantum computing. So in this scheme, what you need is really quantum memories. And thanks to quantum memories, you can remove the need of simultaneous success. So you have an asynchronous preparation of the network thanks to the quantum memory, and that gives you this exponential, this polynomial scaling instead of an exponential scaling if you don't have this resource. You also need to use dedicated photonic sources, which can base today on SPDC and tomorrow on more deterministic sources like quantum dots. So that's one path of research, quantum internet. This is developing very fast. I just want to give you some example at the European level. So we have this flagship project that started 5 years ago during the ramp-up phase, and now the new phase of the flagship. So this Quantum Internet Alliance has a goal, which is to make a first quantum repeater segment of 50 kilometers by next year. So we are working hard on that. And then by 2030, to make 500 kilometers with repeating capabilities. So where we begin to have entanglement swapping between quantum memories. And as you all know also, in Europe, we have EuroQCI with many test-bed deployment in most of the member states. So just to give you one example of the one we have in Paris, this is the Paris network, which is a 50-kilometer backbone from the center of Paris here, so at our university, going to Orange, which is a telco provider in France, which is a trusted node in quantum cryptography protocol they are deploying for now, and up to Saclay, connecting many academic actors and industrial players. So today, this is a quantum cryptography network where we have some deployment of the infrastructure. And the next step, also at the Paris level, will be to go towards entanglement-based network and first field deployment. So that was one path of research. The other path of development is how we can use all this network capability to help the scaling of quantum computing capabilities. The issue today of quantum processor units, of QPUs, are whatever the technique you are using, whatever the qubit modalities, they are currently limited in size. For many technical reasons, the number of qubits you can reach is pretty small. So one path towards scaling quantum computing capability is to interconnect them, exactly as we have known in classical data center. We can think about making quantum data centers with interconnected QPUs. And this is what we call distributed quantum computing, and you can call that also modular quantum computing. And the name of the game here will be also to distribute entanglement between these modules, which is represented again by this entanglement side, having multiple mid-size QPUs with a limited number of qubits, and then how you can interconnect them in this picture. So just a small parenthesis about distributed quantum computing. So the idea is I don't have this QPU here with a large number of qubits today. And later on, if I have more qubits, I would like to connect them anyway to get even more powerful. So the idea is I will start with smaller QPUs and try to realize entanglement links, bell pairs between these QPUs. And then the issue is how I will distribute this monolithic quantum circuit, which cannot be run on these small QPUs. How can I run it on these multiple QPUs? So that's a complex problem where you have to make some graph partitioning. And then you will map back this optimization to sub-circuit partition, and you will have non-local operation between the QPUs. So this is where entanglement enters into the game. You will have entanglement links, which will enable to make some non-local operation, which can be some telegate or some teledata. So basically, communication-based protocol in your cluster of QPUs. So it requires entanglement, as I said, and entanglement is really also here a resource that you want to generate, allocate, distribute, and consume for your compute. So just here what you need to go from this step to this step is what we call a quantum compiler for distributed quantum computing. So it's an optimal partitioner which has to minimize the cost. And what is the cost in this field is the number of entanglement links, the number of bell pairs you have to produce and to generate in your network. So just as a side note, WeLink has developed actually a compiler for distributed quantum computing, which is an optimized version of how we can distribute this algorithm with resource optimization. There will be a paper on arXiv soon next week about efficient gate reordering and how we can decrease, sometimes by orders of magnitude, the number of bell pairs you need to share between these QPUs. Let me give you a bit this picture of a quantum data center. What are the capabilities I need to develop if I want to make that effective? So I show you here two small-sized QPUs. So first of all, most of the QPUs today, they are completely independent. They are completely not able to speak to the outside. They are isolated. So we need to find a way to extract photons, because what we believe is all this entanglement exchange will be via photons. So you need to find ways to extract the photons. So this is what you call in a superconducting qubit a quantum transducer, for instance. You can go from a microwave photon to an optical photon. For neutral atom QPUs, you can use a cavity QED system, which will make you able to use one of the qubits as a communication qubit and then extract a photon, which will be entangled with your QPU. So that's this qubit photon interface, which is very dependent on the platform. You will need quantum memory as synchronizer. I will show you an example. You will have a full photonic entanglement circuit and switching for topology management, allocation of entanglement. And you might want also to have other quantum memories, which will be storing entanglement and releasing entanglement and allocating entanglement on demand in a versatile way in this network. So this is a kind of list of the capabilities. So QPU interface, as I said, to extract the photons or to send photons into the QPU. They are not isolated anymore. You may want to boost entanglement generation by synchronizing the photons coming from the QPUs. You want to deliver entanglement in this reconfigurable network. So this is where quantum memories plays a central role. And you might want heterogeneous interconnects. This is what is will happen in many HPC centers where you will have different kind of providers, different qubit modalities. At certain point, you want them to speak to each other. So for that, you might need to change the frequency. So you will need frequency converter, sure. You might want also to match the wavelength. That's what I said. Match the wave packet. It's very important. At a certain point, you will have Bell state measurement. So you want to be sure that the visibility will be high to make this Bell state measurement. And you might want also, I will show you one example, realize a qubit converter. So where you can change the encoding from DV to CV, for instance, from discrete variable to cat state qubit, to be able to match the different qubit modalities. Let me give you one example of this synchronization of photon via memories. So if you take today microwave superconducting computers, so this is what is represented here, you can develop what we call a quantum transducer, where the efficiency is today pretty limited at the percent level. And then you will go from a microwave photon to an optical photon. And then you want to make a Bell state measurement with these two photons in the middle to make entanglement between these two QPUs. But these photons, they are not emitted at the same time. So the idea of a quantum memory will be to resynchronize them with some heralding coming from the QPU itself. And then you can enhance by this way the rate of success of this measurement. So if you make the calculation with two QPUs like that, the rate is enhanced by the memory efficiency squared divided by the small probability p. So if you take the typical number today with a 1% quantum transduction on the 90% quantum memory, you can get a 2 orders of magnitude enhancement in the rate between your two QPUs. So then you can scale it to more. Then if you think in the midterm to a more complex 2D network, as we have in classical data center. This is a paper by Cisco, for instance, by Quantum Cisco, which is an architectural design. So there are very diverse way of doing a network topology. This is very well known in classical, so FAT3, HyperX, and so on. But this is what you will like at the end, because we can think now of some test bed with interconnection of two QPUs, but in the long term, what you would like is not to have this limited one-to-one connectivity. You would like to be able to have a large photonic interconnect with storage capability, where you will have, at the end of the day, thanks to that, this all-to-all connectivity and dynamical reallocation. And then, as I said, also, you would like at a certain point to be heterogeneous, so with frequency matching, wave packet matching, and qubit encoding matching. So that was that was my introduction. I wanted to show you how networking is a path to scale quantum information architectures. We know it for long distance quantum communication via the quantum internet, but also for next generation of data centers that will include QPU capabilities. So let me go to the lab now, and I want to show you how we developed a few capabilities in this general picture. So this is first a quantum memory. So this is a typical AMO lab. So what you see here in the middle is a vacuum chamber, a glass chamber, where we trap millions of atoms. Here it was cesium atoms at very low temperature. So what we are doing in my group for a long time now has been to work on quantum memories based on atomic ensembles. So no single atom, where you don't know where to catch the atom. Here we are using a very large atomic ensemble. And what you do when you use a very large atomic ensemble is typically you use what we call this collective state, which will lead to an enhancement effect. So when you store a single photon, you will be going to map it by a coherent process, EIT or over protocol. And then you are going to excite one of the atoms, but there is no way to know, even in principle, which photon has been excited or changed level. So what you get is this Gaussian superposition here, which is a collective state. And later on demand, you can read out this excitation. And thanks to this collective effect, all these spins are going to work together. You will retrieve the light in a very well-defined spatio-temporal mode. So I can come with a single math fiber, and I will leave with a single mode fiber at the output. So basically, the picture I like to give is it's really an array of antennas. My spin are my antennas, and I need to control. If we do that, that will be very directive. This is used more and more in 5G and 6G technology, and that will be very directive if you control well the phase between your emitters. And this is what we are doing. We need to control the phase of our quantum superposition. So we are fighting decoherence to extend the lifetime of our superposition. So let me show how we can make with an atomic ensemble a 90% quantum memory. So 90% storage and retrieval. So we did many experiments in the community over the last 20 years on quantum memories, pushing multiplexing. In my group, I focused a few years ago on pushing the efficiency. So which is really the name of the game at a certain point. If you want to synchronize a system, it will be to the power of n if you have n memory. So you want to be very close to unity. So the first thing, the name of the game, when you make a quantum memory, is you want many atoms. So the name of the game is what we call the OD, the optical depth, and this number needs to be very large, a few hundred. So we developed a few years ago a very specific setup with a few recipes where we can have a magneto-optical trap here, which is 3 centimeters long, with an OD close to 500. At the same time, you want to prepare your atoms, you want to keep them cold enough at a few 10 of microkelvin or below in this system. And then we were able, using that, to make a first quantum memory with a storage and retrieval efficiency. So again, what is storage and retrieval? I think I forgot to say it is you store a photon. What is the probability then to retrieve the photon when you want to read it on demand? So it's really in, out. And we got something like 70% at that time with a 99% fidelity for the storage of a polarization qubit. So we were very happy with that, but it was limited to 70%. And actually, we were increasing the number of atoms further, and it was still 70 or even lower. It was decreasing than with the number of atoms. So I won't tell you the whole story, just due to multiple excited levels in cesium atoms we were using. And then you have some trade-off between increasing the efficiency on the memory and paying the price of some decoherence process coming from this off-resonant excitation of the excited levels. So we understood that, we changed the laser, we changed the transition. Basically, we went from D2 to D1 line. And we were able in 2020 to achieve a 90% storage and retrieval efficiency for a single photon, but also for, in this paper, for entanglement. So we are storing photonic entanglement into 2 quantum memories, retrieve it out, and checking that we have also close to 90% entanglement transfer before and after the memory. So that was a few years ago. What we did since then was an experiment with the group of Eleni Diamanti, where we wanted to use this memory in a quantum cryptography protocol. So our starting point was, okay, the memory is pretty good now. We have very low noise, we have high efficiency. We should be able to make a cryptography primitive where this efficiency does matter. There are many protocols where it doesn't matter, you post-select at the end. But there is a one, which is a quantum money, which was introduced by Wissner in the 80s, so one of the first cryptography primitive, where the transmission and the added noise are both contributing to the security threshold. So basically, Eleni did that a few years ago on a full photonic setup. This is a BB84 transaction. So there is between a bank and a vendor. So you send BB84 qubit, and then the vendor can check this information with the error rate of the transaction by this classical channel. And depending on the error rate, he can decide if it's secure or not. Secure meaning there is no double expenses on this credit card. So what we wanted to do is to add in this kind of protocol a memory layer. So where we can store the information and then retrieve it, which is kind of what you want to do for a quantum money card, even if it's for a very short time here. So it's really stringent in terms of the memory performance you need. You need very high efficiency and very low noise. So we did the experiment. So you can find it on arXiv. Where we generate this BB84, we can measure here, we have random number generator here, and then in the middle, we have this specific quantum memory. And then if you analyze the security threshold in that case, this is what you get. This is the error rate, so basically this is related to the fidelity of the memory. I told you we can achieve 99 to 99.5% fidelity after storage. And then the memory efficiency. And as you can see, the secure area is only in this small corner here. So you need to have very efficient memory with very low noise. And we have been able to put an experimental point you see here with an error rate below the percent level and an efficiency close to 80%. So that was the first demonstration of adding a memory layer into a quantum cryptography primitive. All these developments led actually, as I said before, to the founding of a company with my co-founder Eleni Diamanti, which is called WeLink, I said. And actually, WeLink started 3 years ago, and now this kind of quantum memory, you can find them as a product. So we released this product last March, QDrive, which is a memory giving you, it's really plug and play. It's fiber in, fiber out. And what you get is a 99% fidelity and an efficiency above 90%. Actually, in the A&D lab, we got close to 95% now regularly. So the storage time of this first version is up to 200 microseconds. Which is okay for local area network, like the quantum data center I was presenting, which is too short for long distance. But actually, since then, so that was in last March, and since then we are close to the millisecond regime for this quantum memory. Also, something very nice, by using this product, the engineers at Willink were pushing what we can do else with it. And they were able to use it as a pulse shaper. So that was proposed by Michal Lukin a very long time ago, 20 years ago, that if you have a large OD, a long ensemble, you have the full control of your control pulses, we are using EIT, then you should be able to pulse shape. But all that are very stringent requirements, but in this product, it was possible to do it. So basically, they were storing, so what you see as a function of time here, they were storing a pulses, like a 100 nanosecond pulse. They can read it as a 100 nanosecond pulse, and you see the efficiency is close to 100% here. But you can also read it if you want with a very long Gaussian pulse. So that gives you this capability of pulse shaping, actually, I was telling you before. And actually, so that's pulse stretching. You can go from megahertz to 50 kilohertz. But actually, you can put any input and any output with 90% efficiency. So in particular, in the context of network, I can take a photon as an input generated by SPDC, which will have this double exponential decay. I can map it, store it, and then release it with a different shape. And I can match the shape, for instance, of the light emitted by an ion in a cavity, which will be very different and very long. And this is exactly what you want to do in this kind of heterogeneous network. And this is the kind of experiment we want to do also in the Quantum Internet Alliance, where at the end of the day, we want to connect a quantum repeater backbone on some individual node based in Innsbruck on ions. So let me come back to this KIA, this Quantum Internet Alliance. So we are developing, as I said, this 50-kilometer link, which will be telecom heralded. So we have two quantum memories. One will be from the company, from Willink, this product, and one will be the one in my group. So for doing that, so it's a heralded at telecom. So it's a single photonic entanglement that you map into the two quantum memories. What you need also is very specific photon pair sources to exchange entanglement in this network. And in particular, you want sources which are compatible with quantum memory. This is very important to be compatible. I mean, most of the sources you will find, they cannot be matched to light matter systems, which are very demanding in terms of bandwidth, for instance. And then you want something so that you can match to rubidium, and you want the other photon to be at telecom. You want to distribute it in your network. And of course, you want a very large heralding efficiency of your source, because that will give you the rate in your system. So this is something we have developed in the lab. So we have SPDC in cavities based on PPKTP. So they are locked on rubidium D1. So it's very long cavity. Actually, they are something like 3 meters long, because we want a large heralding efficiency. So if you want in an OPO a large heralding efficiency, what you need is a large output coupler that will give you basically the purity of the single photon you can generate, or if you use it in a squeezing operation, that will give you the level of squeezing you can achieve. But of course, I still want the line width of my cavity to be something like 1 megahertz or a few megahertz to be matchable to my rubidium quantum memory. So if I decrease the output coupler, my other way to increase the lifetime will be to make the cavity very long. And this is the case here. It's a 3 meter long cavity. And we did two of them because we want to make swapping in the middle at telecom wavelength. So this is the result. So this is a G12 measurement, for instance. So you see signal on idler, and indeed we are around 2 megahertz bandwidth. And importantly, the heralding efficiency. So I won't detail that, but that's the measurement. But the result of this measurement is that in the single excitation regime, you have a 60% heralding, above 60% heralding into a single mode fiber. So this is really what's going to be used in my Bell state measurement. Just to, I should go fast. I think I'm almost done. Not in my tool, but in the time. Another capability, which is much more exploratory, actually, I would say, is how we can convert qubit encoding. How we can go from DV to CV or from CV to DV. So in my group, we have an experiment on non-Gaussian state engineering. We are using multiple OPOs, multiple heralding, homonine conditioning, all what we can do with that. And by the way, there is a back-to-back paper now, one in Physical Review later, the other one as a companion paper in Physical Review A, where with Radim and his team, Lucas, who is here, Lucas Lackman, we have studied how we can go towards this non-Gaussian coherence and verify non-Gaussian coherence in experimental state. So basically, if you start from fog state, you want to reach this kind of state, and you cannot use displacement and squeezing operation to reach that. That will define your hierarchy. So there will be a talk by Lucas on Wednesday afternoon, tomorrow afternoon, on the poster by Alban Lapras, who is a PhD student in my group this afternoon. So the resource we have been using for a while in the group is hybrid entanglement of light, where we can have entanglement between CV and DV, between single photon qubit and cat state qubit. And we leverage over the years these resources. So, for instance, we have been able in 2020 to make hybrid entanglement between DV-DV entanglement, single photon entanglement, and hybrid entanglement. So at the end, you get hybrid entanglement. And we needed to do that to develop some very specific Bell state measurements, which are based on photon counting, but also on homodyne conditioning. So this is what we published with Akira Furuzawa recently, how to use this hybrid approach combining homodyne and counting to make Bell state measurement and decrease the errors that you can have in this linear photonic Bell state. The most recent paper was to make a teleportation experiment with hybrid entanglement. So basically, the idea was to make a converter where you start from any single photon qubit, and by teleportation, you can map it to a cat state qubit. So very similar to what you have if we want to take a picture of that in terms of classical information, where you will have digital to analog or analog to digital converters. So we were able to measure, for instance, the input DV qubit. You have here their Wigner representation, and here the output after teleportation, and measure what is the fidelity, which was above the classical benchmark. So typically in this experiment, we were able to map two computational bases, starting from DV, ending in CV, and preserving the fidelity. So this is a bit all the capabilities I wanted to show. The last one I wanted to show, but I won't have time to discuss that today, is how you want to extract photons from QPUs. And for that, I believe that nanophotonics is a good way towards integration. And we have two activities in my group, which is to push optical nanofibers, where the atoms are weakly coupled, but we can add Bragg mirrors in this system and enhance the cooperability of this system, and then the nanofiber can be integrated into a QPU. On the other platform, much more exploratory that we are developing, is based on photonic crystal waveguide, where you can enhance without a cavity in single pass the interaction. And how it works is because as you have this structuration in a photonic crystal, the structure is dispersive now. You have a band gap, and close to the band gap, you will have a slow light guiding. And you can use this slow light guiding to enhance the interaction. But very interestingly, also, you have a band gap, so you can use the band gap, work inside, and there is a very interesting panel of protocol you can do if you play with the band gap, because you can tune close to, inside the band gap, the light cannot propagate, but actually there will be a kind of decay length. So you will have at the end a tunable, long-range atom-atom interaction in your system, and that opens possibility also for quantum simulations. So let me go to the, you see, I was trying to show you many things, but just to wrap up. So I wanted to show you today how quantum networking can be a path to scale up our quantum information architectures for two applications, quantum internet and quantum data centers for QPUs. And for that, we need to develop capabilities, and I was showing you a few of them, like this photonic network with storage capability, some photon pair sources which are compatible with network and with light matter interface, how we can make pulse shaping for Bell state measurement for heterogeneous systems, or conversion of encodings. And my last point I didn't make, but I just want to point it out again, that atoms on nanophotonic is a nice path to scale also in terms of integration for quantum linear optics, for quantum simulation, but also for qubit extraction from QPU, which is today one of the missing pieces in these QPUs. So thank you very much.
We have time for short questions. There was one in the back first.
Thank you for this nice talk. Is there a possibility to push the efficiency even higher than 90%? Is there room?
Yes. So you saw in my lab, it was 87, something like that. In the company, 90 is on a daily basis. Very often they got 95%. So actually, if you look the scaling of efficiency with OD, it increased very fast, but then it's kind of a plateau. On the distance between, this 1 minus epsilon at the top depends, for instance, on the decoherence in the ground state. So just having better laser, better phase lock will help to go to be higher. And then there are ways then to use less atoms. If you pulse shape much more at the input, then you can increase.
Is there any more questions?
These cold atom memories work very well in terms of performance, like efficiency, fidelity is very impressive. On the other hand, the bandwidth is like megahertz level. Is this a limitation for the kind of applications you have in mind, or is bandwidth not so critical there?
So actually, they are not limited at the megahertz level. If you have more power in your coherent control pulse, you can push the bandwidth. So our goal is to go to, gigahertz will be difficult in this system, but going to 100 megahertz is really something we are doing now. So going from 1 to 100 is just a question of shaping, of power of the control in your system. And we are doing it because an important goal at the end will be to, as you know, to couple quantum dots to this kind of system. So we are going to meet somewhere.
Okay, and we will have the very last question.
So thank you for the talk. I would just to go back to the first questions. So my main one is, why did you use cesium? So I think you want to increase the optical depth quite a lot, so you increase the density. And I know that interactions in cesium atoms are quite nasty, but is it a source of decoherence, the interaction in cesium atoms? Or?
So I guess I forgot to say that. So in my lab, initially for historical reason, it was cesium. The new experiment we are building on the product from the company, they are rubidium, which is helping a lot in the preparation, and in particular, magnetic field related decoherence. So all that are now rubidium-based experiment and not cesium-based experiment anymore.
As the goal is to couple all of this with optical fibers, will it not be more interesting to choose an atomic species with actually a transition that is more toward telecom wavelengths?
It really depends on the application. If I want to connect to a neutral atom-based QPU, based on rubidium, for instance, that's a good choice. If I want to emit a photon at telecom, yeah, certainly. Quantum frequency conversion is also pretty efficient now. We are working on that in the lab and also in the company, trying to get close to 70% in and out, not intrinsic, but really external efficiency for quantum frequency conversion. And then if you think to this picture of a quantum data center, I won't need to go to telecom, very likely.
Thank you.
Thank you. We have to
Thank you
go
very
on,
much.
so let's thank the speaker again.